This is going to be a presentation of Omar Khayyam's solution to a very specific type of cubic equation. So Omar Khayyam was an Islamic astronomer and mathematician of the 11th century. Sort of interesting to me was that he maybe went against the grain of the maybe very religious culture that he was living in by, on the one hand, challenging the Muslim solar calendar of the time. And he also wrote a poem that had some atheistic sentiments, which I thought was interesting, although he later made a pilgrimage to Mecca to try to clear himself of the accusation of being an atheist. In the world of mathematics, Khayyam contributed primarily to algebra, and he also spent some time trying to prove Euclid's parallel postulate. Very notable in his work within algebra was that he tackled all sorts of cubic equations, and he recognized that they could be at least the what he considered to be cubic equations, which was any cubic equation that had one as the coefficient for the cubed. He recognized that of those cubic equations, there were 27 distinct types, which can easily be seen because he worked with anything of this form is what he considered a cubic, x cubed, where the coefficient is 1, x cubed plus ax squared plus bx equals c, where a, b, and c could be positive, negative, or 0. So that brought about the 27 distinct types that he classified cubics into. And he went on to show that eight of these types can be solved using Euclidean methods. Four have no solutions at all, at least with the tacit assumption that an acceptable solution must be a positive number, and that 14 can be solved by the use of conic sections. That's 26. The 27th was where A, B, and C are all 0, the trivial cubic, which he didn't consider to be an equation at all. So one of the forms of the cubics that Khayyam used or solved with the use of conic sections was this type of cubic, which he stated in this way: cube plus squares plus edges equal to numbers. And in modern notations, we would read that in this way: x cubed plus ax squared plus bx equals c. And he had a really ingenious geometrical solution. And the way that he kind of went about this was that he thought about all of the components of this equation as representing volumes of rectangular solids. And it's really easy to see how x cubed and ax squared can be thought of as volumes because x cubed, of course, is just a cube with side length x. Ax squared is like a rectangular prism with a square base of side length x and a height of a. But the terms bx and c, it's not quite as obvious how those can be thought of as volumes. But with a little reformulation, it becomes a little bit more obvious. So allow p to be the square root of b so that p squared is equal to b. And let q be such that p squared times q is equal to c. Then now bx and c can both be thought of as volumes because bx would be p squared x, so a rectangular prism with a square base of side length p, height x, and then c is a rectangular prism with a square base of side length p and height q. So moving forward, we're going to think of our cubic as x cubed with these new representations: x cubed plus ax squared plus p squared x equals p squared q. And now we can kind of jump into his proof. And of course, with construction proofs, a lot of the actual proof relies on the construction. That's kind of where a lot of the work is done, is actually the construction, and then the proof just sort of falls out. So we'll begin by constructing a line segment BH to represent P. Sorry, this is BH. BH to represent P. So BH is of length P. And we will construct a perpendicular BG, perpendicular to BH, so that BG is equal to Q. We will extend BG past B to D so that BD equals A. And we'll return to these. We actually are not going to work with these assignments until the very end. Like at the very end of this proof, we'll reassign back to the familiar P, Q, and A. But for now, we're just going to work with line segments. So now that we have our BH, BG, and BD, on DG, which is just a straight line, we construct a semicircle with a diameter DG. And we construct this semicircle on the opposite side of DG from H. And the very last thing that we'll do is we will complete this rectangle BHKG, which moving forward, we're just going to refer to this rectangle as BK. So next comes kind of the key element of this proof, which is a hyperbola. In particular, a hyperbola that passes through the point G and has asymptotes of that are BH and HK. So if we can imagine BH being extended vertically and HK being extended horizontally, those will be the asymptotes of our hyperbola that passes through G. And it's important to kind of note, it might seem a little bit like a small detail, but it is important to note that since GK is parallel to BH, which is one of the hyperbola's asymptotes, it follows that this hyperbola is going to pass into the interior of the semicircle and then will pass back out so that it has another intersection point. So yeah, this intersection point right here, Z, which we're going to call Z, this definitely does exist. So once we have our point Z, we're going to make a couple more lines. We're going to draw ZT perpendicular to HK, and we will draw ZA perpendicular to BH. Now, Omar Khayyam then goes on to claim without justification, which is maybe my favorite thing that some of these ancient mathematicians do, is just make a claim without, like, it's just a really obvious claim. He makes this claim without justification that the rectangle ZH, so this kind of tall, skinny rectangle, the area of ZH equals the area of the rectangle BK that we formed on the last slide. So I want to kind of put a little bit more justification in there than Omar Khayyam did. And this is probably the reason that he didn't justify it himself, is because he knew that this had already been proved by Apollonius. So Apollonius's Conics, Book 2, Prop 12 actually proves this. So he must have just felt that anybody reading this proof was so familiar with Apollonius's Conics, it would have been obvious to them. To me, it wasn't obvious. And even knowing the proposition, I've gone to try to Google the proposition and I've had a hard time finding it. I'm sure that it says literally just exactly this about the areas, but I want to put a little bit more justification to it. And the way that I did that was by using, of course, modern algebra. So my method was to imagine that all of this was actually in a Cartesian plot, where the origin of the Cartesian plot was at the center of the midpoint of DG, so the center of this semicircle, the center of the diameter of the semicircle. Um, then I said that, all right, well, this point G is going to lie on the x-axis. Here's the x-axis of our Cartesian plot. G lies on the x-axis. We'll say it's at some point G0. And the other point that we need to kind of put coordinates to is the point H down here, which I said let it be at little h, little k. Then just from that, we can calculate the area of BK. So the area of BK is this length, which is h minus g, times this height, which is 0 minus k, so negative k times h minus g. And if we pass this negative into the h minus g, we get that this area is g minus h times k. So now we just need to prove the same thing for ZH, which takes a couple of steps, but it's not terrible. So our semicircle, of course, has a radius of g, so it's described by the equation, the square root of g squared minus x squared. And because our hyperbola, the asymptotes of our hyperbola run parallel to the axes of the Cartesian plot, we can really think of the hyperbola as being a transformation of y equals 1 over x, with the center of this hyperbola at h, little k, and passing through g comma 0. So the generic form of this would be y equals a divided by x minus h plus k. That's just the generic form of 1 over x with the center at hk. And we solve for a in the usual way because we know that this hyperbola passes through g0. So we just solve for a in the usual way, and we find that a is negative k times g minus h. So our hyperbola is described by this equation, negative k times g minus h, all of that divided by x minus h plus k. So then our hyperbola and the circle intersect at where these two equations are equal to each other. And attempting to solve this out and solve for x, like a closed form solution of x, results in a quartic equation. It's super duper nasty. I played around with it for way too long before realizing that I actually don't need to figure out that point. I know that the point does exist, so I just say, okay, let the solution be x naught. So x naught is a solution of this, then our point z is at x naught, comma, the value of our hyperbola at x naught, which is just plugging in x naught into the denominator here. So now I've got coordinate points and I can take the area of ZH. So the area of ZH, well, its width here is h minus x naught. Um, and its height is this value at x naught, so this negative k times g minus h all over x naught minus h plus k. That's this value right here, minus k. So the plus k and the minus k cancel, and then working with this over here, we've got this x naught minus h in the bottom. If I factor out a negative here, then the negative and the denominator and numerator cancel. And also the bottom becomes h minus x naught, which cancels with this other h minus x naught to give us exactly k times g minus h, which is what we found the area of bk to be. So, of course, Omar Khayyam was perfectly correct. Nobody ever doubted it. I mean, maybe I doubted it for a second. Okay, I'll be honest. I doubted it for a second, but I doubt no longer. He was right. Okay. Um, so we found that BK is equal to ZH, but notice that they both, ZH and BK, those rectangles, they both share in common this white rectangle right here, BHTL. So if we subtract out that common rectangle, then we find that LK, this purple rectangle, is equal to ZB. So the green and the purple areas are equal. And in Book 6 of Euclid's Elements, Prop 12 states that if two parallelograms are equiangular, which we know that these are because they're both rectangles, if two parallelograms are equiangular with equal areas, which we also just proved, then the sides about the equal angles are reciprocally proportional. So what does that mean? That means that ZL right here, ZL is to LG as TL is to BL. But notice that TL is equal to HB. So we have that ZL is to LG as HB is to BL. And if we just square both sides, the equality is maintained. So ZL squared is to LG squared as HB squared is to BL squared. And then Khayyam goes on to make another claim, which he kind of justifies. He says that, all right, well, ZL squared is to LG squared as DL is to LG. And I kind of want to read what's written in the text because it sort of makes me laugh. It says the proportion of the square of ZL to the square of LG is equal to the proportion of DL to LG because of the circle. So he does kind of justify this, but it still sort of begs the question because I was sitting there being like, what do you mean because of the circle? Um, and I don't know, maybe there's another proposition that actually leads directly to this, but here's how I went on to justify that. So, and it starts with Prop 31 of Euclid's Elements from Book 3, which states that a triangle inscribed in a semicircle has a right angle along the circumference. So this triangle GZD has a right angle at Z. This is also called Thales' theorem, super famous theorem. And then another theorem from Book 6 of the Elements, Prop 8, we can deduce that if a perpendicular is drawn from the right angle of a triangle, then that perpendicular is a mean proportional between the segments of the base, meaning that DL is to ZL as ZL is to LG. So if we just cross multiply here, we get ZL squared equals DL times LG. And if we divide through by LG squared, we get ZL squared over LG squared is equal to DL over LG, which is, again, what we set out to prove. So once again, he makes a claim that was 100% true. So we have that. Um, let's see. And this actually is kind of tying together two. Um, sorry, I need to move back up. This is actually tying together two equations that we were working with. So this first one from two slides previously, that ZL squared divided by LG squared equals HB squared over BL squared, and then ZL squared over LG squared also equals DL over LG. So we have all of this right here, and the key parts are the endpoints, that HB squared over BL squared is equal to DL over LG. And again, if we just cross multiply, this gives us that HB squared times LG is equal to BL squared times DL. But notice that DL is equal to BL plus BD. So we can rewrite the right-hand side as BL squared times the sum BL plus BD. And if we distribute this BL, we get that the right-hand side is BL cubed plus BL squared times BD. And next, if we, to both sides of this equation, if we add HB squared times BL, which sort of feels like an arbitrary thing to add, but it actually is like the very last piece that we need to solve this cubic. If we add HB squared times BL, then on the left we have HB squared times LG plus HB squared times BL is equal to BL cubed plus BL squared times BD plus HB squared times BL. But notice on the left-hand side here, we can factor out HB squared, and we're left with the sum LG plus BL. But notice that LG plus BL is just BG. So the left-hand side can be written as very succinctly as HB squared times BG. So our equation now is HB squared times BG equals BL cubed plus BL squared times BD plus HB squared times BL. So here's that same equation just rewritten once more on this slide, kind of for convenience. And recall that at the very beginning of this, we made some assignments. We said that BH is equal to P, BG is equal to Q, and BD is equal to A. And if we finally make the assignment of allowing BL to be equal to X, then we can rewrite our equation, the one at the top here, as P squared Q equals X cubed plus AX squared plus P squared X. And remember, once again, that we chose P and Q specifically so that this equation right here is the same as C equals X cubed plus AX squared plus BX. So with X being set equal to BL, what all of this is saying is that BL, this length right here, is the solution to our cubic. So not only did we find a solution to the cubic, we also proved that there always exists, under these circumstances, there always exists a solution to this cubic, because this is always going to be some kind of positive distance. So yeah, not only did we prove that the solution always exists, we also found the solution as well.